Here I will give an overview of how to implement an accurate conversion method for object detection and segmentation with BrainCog. In the previous video, we mentioned that in classification tasks, residual information, that is clip error and quantization error, and pooling operations have a large impact on the performance of converted spiking neural network. The residual information problem can be effectively solved by using burst spikes, and the exact max pooling can be achieved in the converted SNN using lead pooling. Experiments show that the spikes of inactivated neurons problem has a small impact on the performance of the classification tasks. However, we visualized the approximation of the multi-layers of VGG16 and find that the total synaptic current received by the SNN always has some error with the activation value of the ANN, showing a fixed drift or a gradually increasing error, which is not conducive to the implementation of accurate conversion. Another obstacle to achieving accurate conversion is the quantization error, which arises because SNN uses the firing rate for information representation and cannot output continuous real values. We visualize the ratio of the two errors during the conversion process and find that the quantization error can gradually converge to zero as the simulation time grows. In contrast, the SNN error exhibits slow growth. Therefore, dealing with the SNN error is crucial to the conversion process. Then, how do you find which neurons to have SNN errors anymore? We find that the conversion process in general is relatively stable in terms of the variation of its interspike interval. However, the spike chain is not uniformly distributed, and its firing rate is active around the ANN activation value. From this figure, we can see that most of the curves can maintain a stable trend despite their more frequent jitter. So we propose by calibration to solve the SNN problem effect on conversion. We monitor the moment of arrival of each spike. To reduce computational stress, we slightly update the interspike interval of each neuron and set the allowance as the maximum limit of the interspike interval. After the neuron issues a spike and there's still no spike activity after the expected interval and allowance, the neuron will issue a negative spike for spike calibration. It is very effective for the SNN problem because after each spike issued, the memory potential of the neuron corresponding to the negative activation value in AN tends to be more and more negative, and the probability of its issuing spikes becomes smaller. In addition, the conversion often use the p-norm method for weight normalization. Previous methods usually use empirical setting to achieve robust results. We use Bayesian optimization method for this hyperparameter. Specifically, we minimize the KL divergence of AN and SN outputs on a portion of training data for searching for the optimal p-value. The Bayesian hyperparameter optimization method can avoid empirical settings and find the optimal value efficiently. Combine the above method, we achieve a more accurate approximation of the AN output, and the experimental results show that the output of the SNN can achieve an accurate fit to the AN output with calibration. Thus, helps us to achieve better results in detection and segmentation tasks. In BrainCog, we can easily enable this feature by simply setting spike collapse allowance. The default value of 0 means that this feature is not used. Here is the work related to this video for your inference. Thank you very much.